Hello everyone. In this video and the following few, we are going to tackle the issue of optimum portfolio weights. Optimality can be defined differently by different investors. For some, optimality is achieved when a portfolio yields minimum risk. For example, for elderly or retired people, preservation of capital may be the primary goal. They may not go after growth too much and may wish to have highly conservative investment portfolios. Other investors, the ones who are relatively younger, may look at optimality in terms of risk and return. They may want to arrive at a minimum risk for a given desired return. They are the ones looking at a higher potential growth in their investments and may seek some capital gains. We can therefore classify our investors into categories in terms of optimal portfolio weights. So what I've done here is I've written optimal W or optimum W, where W stands for portfolio weight. And we have our three classifications here. This set of people focusing only on preservation of capital, so their objective is to minimize the risk. And these two set of people want to look at their complete portfolio performance. Some of them want to minimize risk, but at the same time they want to ensure that they derive a given level of return. Others want to look at it differently. They want to look at their overall portfolio performance in terms of Sharpe ratio. We also know this as the reward to volatility ratio. On the numerator, we have the reward, which is the excess return, and on the denominator, we have the volatility as measured by the standard deviation of the portfolio. In this video, we will be looking at the first position, this one here, the risk minimization only, for a two-asset portfolio. In later videos, we can extend this framework for n-asset portfolios as well. Let us begin by writing our portfolio variance. We know that portfolio variance is equal to W1 squared times the variance of returns of the first asset plus W2 squared times the variance of returns of the second asset plus 2 times W1 times W2 times the covariance between the returns of asset 1 and 2. We have shown in a previous video that the formula that we have written above can also be written in the a plus b whole squared format, which means W1 times standard deviation of 1 is going to be our A term, and W2 times standard deviation of 2 is going to be our B term. This also means that if we want to write the standard deviation of the portfolio, we just have to drop this 2 from here. So the standard deviation of the portfolio is going to be W1 times the standard deviation of 1 plus W2 times standard deviation of 2. We also know the relationship between the covariance of returns and the correlation coefficient. Let me write it here just in case. Covariance between 1 and 2 can be written as the correlation between the returns of the two assets times the product of their respective standard deviations. We can now have three possible scenarios. Number 1, when the correlation between the returns of the two assets is +1, which means we are looking at two assets the returns of which are perfectly positively correlated. Second, we could move to the other extreme, where the correlation coefficient between their returns is perfectly negatively correlated, is perfectly negative, that is -1. And then there could be a third possibility, which could be that the correlation coefficient may be between the two extremes of -1 and +1. Let us deal with these three possibilities in sequence. When the correlation coefficient between the returns of the two securities is +1, there is no diversification, because for a meaningful diversification, we should combine those assets together which have as less correlation amongst their returns as possible. Therefore, in this case, there is no question of optimum weights. If the correlation coefficient between the returns of the two securities is +1, by combining these two securities or two assets, we are just adding on to the risk that we already have. Therefore, the standard deviation of the portfolio is going to be this. If we are already tolerating this amount of risk from the first asset, then combining this asset with another positively correlated asset is just going to add on to our risk. So there is no diversification benefit. There is no risk minimization here. What happens when the correlation between the returns of these two assets is perfectly negative, -1? In this case, a perfect hedge is possible. Let us see how. Let us begin by first of all writing the variance of the portfolio in this case. In this case, we can write the variance of the portfolio as W1 times standard deviation of 1 minus W2 times the standard deviation of the returns of the second asset whole squared, which would give us a standard deviation of W1 times standard deviation of 1 plus minus W2 times the standard deviation of the second asset's return. We want to minimize our risk. How low do we want it? 0 if we can. No risk is the best option. So what we are going to do is that we are going to set this definition of standard deviation equal to 0 and then solve for the optimum weights. Let us write the definition of standard deviation here. And set this equal to 0. This means that W1 times standard deviation 1 is going to be equal to W2 times standard deviation of 2. What we need to do now is to write this W2 also in terms of W1 and then solve the equation for W1. This is going to be easy because this is a two-asset portfolio. W2 is simply going to be equal to 1 minus W1. Why? Because W1 plus W2 must be equal to 1. The sum of weights must be equal to 1. Let us see what we can do now. We have W1 times standard deviation of 1. It was a 1 here too. W1 times standard deviation of 1 is going to be equal to, let's multiply out the right hand side, standard deviation of 2 minus W1 times standard deviation of 2. Let us write the W1 terms together. So we have W1 times standard deviation of 1, and we are going to take this guy over to the other side. What we have on the right hand side now is only the standard deviation of 2. We can write the left hand side as this. And from here we can easily write W1 as being equal to the standard deviation of 2 divided by the standard deviation of 1 plus the standard deviation of 2, which also means therefore that W2 is going to be equal to 1 minus W1. These are the optimum weights for a zero risk portfolio if the correlation coefficient is -1. Let us move to the third possibility. In reality, it is not likely that we are going to find two assets whose returns are perfectly positively or perfectly negatively correlated. Therefore, when the correlation between the returns of two assets is between -1 and +1, the standard deviation of the portfolio will have to be this. We are going to write the square root of variance. So let me do that here. And we raise this to the power of half because we are taking the square root. Let us also write W2 here and a W2 here in terms of W1. So what we have is W1 squared times variance of 1 plus 1 minus W1 whole squared times the variance of 2 plus 2 times W1 times 1 minus W1 times covariance between 1 and 2. All this to the power of half. Let us now simplify this by opening the relevant brackets. W1 squared times variance of 1 plus, let us now open this square. What we are going to get is 1 plus W1 squared plus, or minus rather, 2 times W1. And this is being multiplied with the variance of 2 plus, let us multiply out this term now. 2 times W1 times 1 times covariance between 1 and 2 minus 2 times W1 times W1, this gives us W1 squared times covariance between 1 and 2. And all this is going to be raised to the power of half. Let us continue. There is this bracket to be solved. Let us do that as well. So we have W1 squared times variance of 1 plus variance of 2 plus W1 squared times variance of 2 minus 2 times W1 times variance of 2. Then we have this term 2 W1 covariance 1 2. Then we have this term let us raise this to the power of half. We want to minimize our risk, and ideally we want it to be 0. Whether we get to 0 or not is a different question, but that definitely is our attempt. So what we are going to do is, we are going to take the partial derivative of standard deviation of the portfolio with respect to, let's say, W1, and we are going to set it equal to 0. From the resulting equation, we are going to solve for W1. Once we have W1, W2 is simply 1 minus W1. So let us write down the partial derivative of the standard deviation of the portfolio with respect to W1. Let us give ourselves some space here to write. So if we look at this expression, we are going to see that we are going to have to apply the chain rule of differentiation, because this inside function here has been raised to the power of half. So what is the chain rule? The chain rule is that we differentiate the outside function and then we multiply the result with the derivative of the inside function. So let us first of all deal with the outside function. So we are going to write here 1 over 2 times the inside function is going to be written as it is. So we write here W1 squared times variance of 1 plus variance of 2 plus W1 squared times variance of 2 minus 2W1 times variance of 2 plus 2W1 times covariance between 1 and 2 minus 2W1 squared times covariance between 1 and 2. And the exponent now is going to be half minus 1, that is minus 1 over 2. We are going to have to multiply this whole thing by the derivative of the inside function. This is our inside function. So let us write the derivative of the inside function here. What do we get from this term? We get 2W1 times variance of 1 plus, what do we get from here? We don't get anything. What do we get from this term? We get 2W1 times variance of 2. What do we get from this term? We get 2 variance of 2 plus, what do we get from here? 2 times covariance between 1 and 2. And then let's look at the last term here. What we get from here is 2 times 2 is 4 times W1 times covariance between 1 and 2. So we have differentiated. Now we need to solve this by setting it equal to 0. We need to solve this for W1. But it looks pretty messy at the moment. Let us try to simplify this a little bit more. This item here, this whole term in the square bracket, has been raised to the power of minus half. This means that if I want to write this in the denominator, the power is going to change to positive. So on the numerator, I'm going to have this term here, and on the denominator, I'm going to have this term here with a positive half power. And outside the bracket, we have 1 over 2. So let us write that and see what we get. The numerator is going to be this term. It's going to be fairly long. So 2 times W1 times variance of 1 plus 2 times W1 times variance of 2 minus 2 times variance of 2 plus 2 covariance 1 2 minus 4 W1 times covariance between 1 and 2. And on the denominator we are going to have this term but with a power of half. So let's write that again here. W1 squared times variance of 1 plus variance of 2 plus W1 squared times variance of 2 minus 2W1 times variance of 2 plus 2W1 covariance 1 and 2 minus 2W squared of 1 times covariance 1 and 2. All of this we can set equal to 0. Now let us see what we can do. We have a 2 here, so it's going to cancel out. So this 2 is going to go away, this 2 is going to go away, this 2 also vanishes, this 2 also evaporates, and here instead of a 4 we are going to have a 2. Also, if we take the denominator onto the right hand side, it's going to get multiplied with 0, and therefore that is going to go away as well. So we are seeing some light at the end of the tunnel. Let us write down what we have now. We have W1 times variance of 1 plus W1 times variance of 2 minus variance of 2 plus covariance between 1 and 2 minus 2 times W1 times covariance between 1 and 2, and all that is equal to 0. Let us write the W1 terms together. W1 times variance of 1 plus W1 times variance of 2, and we have a W1 term here, so let's write it first. 2 times W1 times covariance between 1 and 2, and the remaining stuff we can take it over to the right hand side, which is these two items here. So right hand side is going to be variance of 2 minus covariance between 1 and 2. This means that the left hand side could be written as this. Now we can write W1 pretty easily. W1 is equal to variance of 2 minus covariance between 1 and 2, all divided by this term here, which is variance of 1 plus variance of 2 minus 2 times covariance between 1 and 2. And W2 is equal to 1 minus W1. These are the optimum weights for risk minimization in case the correlation coefficient between the returns of the two securities or two assets is between -1 and +1. See you next time.